Let's try this example. Let f of x equal to 1 if x is greater than 0, 0 if x is equal to 0, and negative 1 if x is less than 0. Is f of x continuous at x is equal to 0? Now this is a piecewise function, so you might find it helpful to graph it. You don't need to graph it, but graphing gives you an idea of what it looks like and you can get a feel if it's a discontinuity or not. So let's start by getting a graph for this function. So when you graph piecewise functions, remember you graph piece by piece by piece. So we look at the first part. F of x is 1 when x is greater than 0. So that means f of x is 1 when x is greater than 0. It's not equal to 0, so there's going to be an open circle at x is 0. And every x value bigger than 0, y will be 1. So that's the first piece of the function. Now the second piece says f of x will be 0 when x is 0 and just 0. So that's just a point. That's the point x is 0, y is 0. So we put the point there. And for the last piece of the piecewise function, f of x is equal to negative 1 when x is less than 0, not less than or equal to, just less than. So you put an open circle at 0, and everything less than 0, all the x values less than 0, the function is negative 1. So now this is the graph of f of x. So we start by looking at the 3 laws of continuity. First law, does the value at 0 exist? So you're going to substitute 0 into the function. In this case, you could look at the picture. F of 0 is 0. You also, if you didn't draw the picture, you would look at the piecewise function. So at 0, f of x is 0. So a value exists. Great. Second law, does the limit as x approach 0 of f of x exist? Now remember, in order for a limit to exist, the limit on the left is equal to the limit on the right. So this means the limit as x approaches 0 from the left has to equal the limit as x approaches 0 from the right. So if you looked at the graph, as you approach 0 from the left side, f of x is equal to negative 1. As you approach 0 from the right side, f of x is equal to 1. That's not true, right? Negative 1 doesn't equal 1. So therefore, the limit as x approaches 0 of f of x does not exist, and it fails to be continuous. So to answer the question, is f of x continuous at x is equal to 0? You say no. F of x is discontinuous at x is equal to 0 because the limit as x approaches 0 of f of x does not exist. Now, if you didn't use the graph, you could have also saw the second law fails by looking just at the piecewise function, but you'd still have to break it up into the 2 limit pieces. So this top piece gives you the limit as x is greater than 0, right? So that means as x approaches 0 from the right. And the bottom piece is as x approaches 0 from the left. So at times it's easier to see the graph, especially when it comes to limits approaching left or right. But you can do it here as long as you can fully understand and see the less than and greater than pieces. Sometimes you'll be asked to find the points of discontinuity of a rational function, and they won't give you the value a to check. So you have to find it first and then check it. So a few things to be mindful of. A rational function is discontinuous where the denominator is 0. So this is your key piece that you're going to want to look at each time. And it's continuous otherwise. However, a rational function is continuous on its domain because remember, if a denominator is equal to 0, then that point where it's equal to 0, that's not a value in the domain anymore. Because remember, domain issues in the domain, we said that there's places where the domain can exist, where the denominator is equal to 0, where a negative is under the radical. So in those cases, that's where you have no domain in those x values. So if you're going to find one of those places where the function's undefined, that actually ends up being, it's still discontinuity, but the function is still said it's continuous in its domain. So they're not necessarily asking you other than find where the function is discontinuous. And you're still going to check where the denominator is equal to 0. And those will be the places where the graph is discontinuous. Because when you graph it, you'll still have to pick up your pen to graph it. But the function's continuous on its domain because its domain doesn't have that value in it because it would make it undefined. Okay, so let's look at 2 examples. Find the point of discontinuity. So if you're given a function, look to see if it's a fraction. If there's a fraction there, look where that denominator is equal to 0. So you take the denominator, x squared plus 2x minus 8, and you set it equal to 0. You factor it. Factors of 8 that are subtracted give you 2. 4 and 2. The signs have to be different. The bigger one has to be positive. When you set these both equal to 0, you're going to get x is equal to -4 and x is equal to 2. So there are 2 points of discontinuity for -4 and 2. So the question only asks you to find the points of discontinuity, and you did. Let's look at the third example. Find the point of discontinuity. Again, it's a fraction, so take your fraction and set it equal to 0. However, this can never be 0, right? If you tried to solve it, it's not a difference of perfect squares. You can't do x plus 2x minus 2. You might want to bring the 4 over, but then notice that you get -4, and then you get the square root of -4, and that's imaginary, and that's not any of the numbers that we're working with here. So there's no solution here. Which means that h of x is continuous everywhere, where f of x is discontinuous at -4 and 2. Sometimes you're asked to find the discontinuities of piecewise functions or case-wise functions. In these cases, you have to figure out, well, where could this discontinuity occur? Notice that each of the cases, or the pieces of the case function or the piecewise function, are polynomials, and we know that polynomials are continuous everywhere. So it's not going to be within those, but it may happen here at the break where the pieces are attached. So that's where you want to focus your attention. So you want to see if it's discontinuous there. So you're going to check using the 3 laws of continuity, and if it fails, then you know that it's discontinuous at that point. You could either graph it or use the 3 laws. I'm going to use the 3 laws here. So the first law says, what is the value at 3? And notice that this piece of the piecewise function has the equal sign. So you're going to plug in 3 here. And you get 9. So the value at 3 is 9. The second one says the limit as x approaches 3 of f of x. Now remember what we said, the limit on the left is equal to the limit on the right. So limit as x approaches 3 from the left of f of x is determined by the bottom piece, less than 3. So when you substitute 3 into the function, you get 9. And then look at the limit as x approaches 3 from the right. You get x plus 6, so that's going to be 3 plus 6, which is 9. The limit on the left equals the limit on the right. Therefore, the limit as x approaches 3 is 9. So then you look at the third rule of continuity. It says the value equal the limit. So we say the limit as x approaches 3 of f of x is equal to f of 3. They're equal. Therefore, are there any discontinuities here? No. F of x is continuous.